what will make this the biggest it can ever be? If this number right here is 1, right? Because cosine, the biggest it can be is 1. And the way that you get cosine to be 1 is by letting the angle be 0, right? Yes? That means that the angle, to get the biggest possible directional derivative, the angle between your gradient vector and the direction that you're pointing must be 0. So think about that. This is the profound statement. I'm up here and I'm like, okay, which way do I point? Which way do I point? Okay, let's call this u. That's the direction that I'm trying to point, right? And then I've got this gradient vector, which seems to have nothing to do with this, right? The gradient vector is the partial derivatives. And then someone's telling me to point in a direction. I'm saying, which way do I point so that I get steepest thing? Well, it turns out to get the steepest, you need the angle between these two vectors to be what? 0, which means that you must be pointing in the direction of the gradient. So the gradient vector itself is the direction that you should point to get your steepest descent. And that, to me, is amazing. All right? Because that means if you can calculate the gradient, then you know which way to point to get steepest descent. So this is the summary of it right here. Maximize the directional derivative. The maximum value of the directional derivative, the maximum value, is the magnitude of the gradient. The length of the gradient vector is the steepest slope you're ever going to have. And it occurs when we point in the direction of the gradient. Remember that. That's a big note right there. So here's an example. We have this function of two variables. First, let's find the direction as an angle of the maximum rate of change at 0, 0. So you've got some surface sitting up here, floating around here. It's not really floating. And you're at the origin, right? 0, 0. You go up to the function. Somewhere on the function you're standing there. And I'm asking you, which way do you point? Tell me which way you point so that you would get the maximum directional derivative. What do I have to do? I just have to find the gradient. That's all I have to do. Okay? So what's the gradient of f? Well, it's partial of that with respect to x, which is cosine x minus y minus sine x, right? So you have to do derivative of each of those, right? So derivative of sine of x minus y is cosine of x minus y. Derivative of the inside of this is just 1, plus the derivative of cosine x, which is negative sine x. So that gives you this. Then that's your partial with respect to x. Partial with respect to y is, be a little careful here, cosine of x minus y, but then derivative inside is what? Negative 1. So it's negative cosine of x minus y. And then derivative of this piece, 0, because x is a constant. So that's it, right? That's my gradient vector. All I need to do now is plug the point in. If I take the point 0, 0 into that, that will be the direction I should point, right? Because this is a vector. The vector gives me a direction. So cosine of 0 is 1. Sine of 0, 0, so there. Cosine of 0 is 1, but then negative, so negative 1. That's it right there. That's the direction I should point, right? So this goes back to like that domain picture. We were sitting here, we were at 0, 0, and then normally, like what I've given you in the past, I told you what direction to point, right? I gave that to you. This question is asking which direction do I point for steepest descent or steepest rate of change. It's telling me to point here. So I point 1, negative 1, 1, negative 1. I point that way, and that's going to give me the steepest descent. I wanted it though as an angle, not as a vector. So what is that as an angle? So to answer this question, what is it? You say negative as an angle, not the point that you're at. Relative to the x-axis, right? That's the angle I should point. If I want to have the steepest ascent, what I need to do, standing at 0, 0, is I need to point negative 45 degrees, pi over 4. You could make it relative to the y-axis, but then everyone would be like, why? Everything's always been relative to the x-axis, But you could. Just make sure you state it. That way there's no confusion. We good? That answers part A. What about part B? Find the maximum rate of change. So what is that maximum rate of change? It's the magnitude of that derivative. So all you have to do is take the magnitude of this. Square root 2? Root 2. Come on, this has got to be somewhat amazing. No, only to me, I guess. Only to me. You've got this surface. You're standing on it. You're trying to figure out where to go that you have the steepest descent. I can tell you which way to point, and I can tell you that's the steepest descent you're ever going to get. Root 2. That's it. You point in any other direction, it's going to be less. And it didn't take a whole lot of work for me to be able to tell you that. And then what I could do is I could move in that direction, right? I start moving in that direction, and I say the same thing at the next point I get to. And that would give me another direction, wouldn't it? And I keep doing that as I move, and eventually I'd be at the top, wouldn't I? And that's where you have, like these contour maps. If you look at a contour map, we talked about this last time. Contour map, works where each of these lines represents like an elevation. So maybe this is like sea level, 0 feet off the ground. This is like 10 feet. This is like 20. This is like 30, right? Then if you walk around a contour line, you never change altitude, do you? If you walk perpendicular to a contour line, you're walking in the direction of the gradient vector. That's what you're doing. And if you follow there's an infinite number of contour lines. We only show some of them. But if you follow all of the gradient vectors throughout the entire picture, then you'd start maybe down here. It would take you through, and it would take you up to the top of the hill. And that would actually be the shortest path up that hill, because it's the steepest descent. Right? Yes?
Can you explain one more time how we got that pound for?
I'm just looking at this angle right here, relative to the x-axis. This is 1, negative 1. This is that vector. Yeah. Yeah, just using the fact that it's, triangle 1, 1. Yeah. So let's just say, just for the sake of demonstration, okay? Let's just say that we would have got something like this. This ought to be good. What if we got a gradient vector of negative 4, negative 7? What would the angle be? So you would come over here, and you'd be at negative 4, negative 7. You'd be down here, right? So you could make a triangle, couldn't you? You could make a triangle out of that? It would look like this. Negative 4, negative 7. You're trying to find an angle here? So what would you do? Arctangent. You'd use the arctangent on your calculator. It's the arctangent of the y-coordinate over the x-coordinate. What would you get? Did you try it? What did it spit out? 60.25 degrees. So if you do arctan on your calculator of negative 4 over negative 7, what was it again? 60 point what? Oh, I just drew it wrong. Negative 4 here and negative 7. Thank you. Yeah. Is that what you had done?
Yeah.
Okay, so what is it? 68?
No,
60.25 degrees. Is that the correct answer?
No.
No, because that's actually just this angle. Your calculator doesn't know you're in the third quadrant. So you'd have to add 180 to that to put you over there. So you'd be a little careful with that. That would be, that's stuff from pre-cal though. We always have to be careful with that inverse function on the calculator, right? Those darn domain restrictions mess everything up. This problem is very similar to the one we just did. I think this one might be a little easier. Well, that's exactly the same, isn't it? Same instructions?
Yeah.
Okay, so I'll let you do that on your own. I think that partials are easier on that one. Yeah? Ooh, now that one. Let's see about this one. Here's a function of 3 variables. Find the directional derivative at this point in this direction. So this is what we started class with. Directional derivative, I give you a vector. You've got to go through and make sure first that this is a unit vector, right? And then go through the whole computation. Then it says to find the magnitude of the gradient at the same point. So this directional derivative is giving you some instantaneous rate of change at that point, right? If we're pointing in a certain direction. This is also giving you an instantaneous rate of change at that same point. Which of those is going to be larger, A or B? B, it has to be. The gradient's always the biggest rate of change you're going to get. The magnitude of the gradient is always the biggest rate of change you're ever going to get. So, do you want me to work this? Yes? Okay. So let's do part A. I'm going to make this a little smaller. Or you know what? I'll go like this. There. So for part A, I need the directional derivative, right? The directional derivative in the direction of v of f of x, y, z should be equal to, why am I using this marker? Should be equal to a times the partial of f with respect to x at x, y, z plus b times partial of f with respect to y at x, y, z plus c times partial of f with respect to z at x, y, z. That's just the definition of the directional derivative. What are a, b, and c? Is it 1, 2, negative 1? No, that's not a unit vector. This is not a unit vector, is it? I have to make it a unit vector first, or else it's all going to be off. So what is the length of that vector? Root 6. So if I take this and I'll call it u. How about that? I'll just scale this 1 over root 6, 2 over root 6, negative 1 over root 6. Now that's a unit vector that points in the same direction as v. And so I should come over here and not call this v anymore, right? I should call this u. I was doing that intentionally. I wanted you to accidentally stumble into that, to remind you must make it a unit vector. Then I need partials. Are we going to do partials on that? That's going to be pretty easy, I think, hopefully. Let's see. Let's go ahead and start writing this down. A is 1 over root 6. And partial of f with respect to x is sine yz. Then I have plus b, which is 2 over root 6. And then partial of f with respect to y, which is x cosine yz times z. Right? Ignore the x, because it's a constant. What's derivative of sine of yz? Cosine yz. Then derivative of what's inside with respect to y? Z. So it's actually going to be xz cosine yz plus c, which is minus, so minus 1 over root 6. And now the derivative of this with respect to z. So xy cosine yz. Good. And now I'm going to plug in 130, right? So the directional derivative in the direction of u of the function at 130 is 1 over root 6 sine of, yes, sine of 0, right? Because z is 0. That's all gone, isn't it? Plus 2 over root 6. Yes, 0 again. Minus 1 over root 6. Right, this one's 0 because z is 0, right? Okay. This one, not so much, right? And so 1 times y, which is 3. Cosine of 0 is 1. So 1. So this is just going to be negative 3 over root 6. Questions? No? Okay. Part B. What's the magnitude of the gradient vector at 130? Well, we know what the gradient vector is, right? We actually got the partials already. So let me just write down what the gradient vector is.
Wait.
Whoa.
For
What? Did I mess?
for this one, xz cosine 0, or cosine yz, shouldn't it be 2 root 6 there? Oh, z was 0.
Z was 0.
Okay, never mind that.
That saves us. That saved me.
Got it.
Yeah.
Wait, no.
No,
Wait, wait.
Thank you.
no, I've made mistakes before. Wouldn't be the first time. Okay, magnitude of the gradient. So the gradient vector, I just erased it. Absolutely wonderful. The gradient vector,
That's why I said wait.
yeah. What was it? X sine yz? So sine yz, right? And then it was yz, and then xy, cosine yz. So that's the gradient vector right there, right? And all I need to do now is plug in the point 130. The gradient at 130 turned out to just be, well, this was 0, right? And this one was 0. And this one turned out to be 3, right? That's not the magnitude of the gradient. That's just the gradient. I need its magnitude to find the maximum rate of change. So the magnitude of the gradient of f, and this one's an easy